The goal of the class today is to present the narrow escape time calculation in dimension 3. So these follow the classes of dimension 2. So let me remind you the context of this problem. We are interested in the mean first passage time for a Brownian particle to escape inside, moving inside the sphere, to escape through the small hole here, the small patch, which can be a small disk or a small ellipse or any convex shape on the surface of a domain. So what we are going to see today is that the mean first passage time, tau, can be expressed asymptotically in the limit of a small. A is the radius of the small patch, V is the volume, and D is a diffusion coefficient. So tau equals V divided by 4AD, and then we have the leading order term, which is 1, plus another term which is of the order of log of 1 over A, and h of 0 is the mean curvature. So this is the mean curvature at the center, let's call it O, at the center of the hole, which is given here using the principal curvature lambda 1 and lambda 2. And then there is a third term which we are not going to describe here. This is the order 1 term, and basically this term contains the information about the initial position of the particle, the Brownian particle, when it started moving. This has been calculated for the sphere using the regular part of the Green's function by the group of Michael Ward in University of British Columbia. So now we are basically ready to start the equation. So this is the narrow escape time calculation in dimension 3. And the first part here, we're going to focus on the leading order term. So to calculate the leading order term, let me remind you the mean first passage time equation, which is d Laplacian u equals -1, u equals 0 on the absorbing part, call it d omega a, and reflecting boundary condition, which is du dn, equals 0 on the reflecting part. And we assume here that the absorbing part is simply a small disk of radius a, such that the total surface is pi a square. So to solve this, we are going to introduce the Neumann function, which is solution of Laplacian n equals minus delta plus the volume of the domain. So the domain is omega. So this is omega. And we have here the absorbing part, d omega a. And the Brownian particle here can escape, can move by Brownian motion until it escapes here at the small hole, and it is reflected at any other place. So the Green's Neumann's function is solution of dn derivative with the external normal, which is equal to 0 everywhere on the boundary. And this is inside the domain, where the we can call it y. So this is a delta Dirac at point y. So note that to solve this, we will need what is called the flux compatibility condition. So the compatibility condition which state that the integral of du dn over the absorbing window is equal to minus omega divided by the diffusion coefficient. And this is just obtained by integrating this equation over the entire domain. Now, from the mean first passage time equation and the Green's function, we can use Green's identity. So Green's identity is n Laplacian u minus u Laplacian n. So if we integrate this over the entire domain, omega d volume, this is equal to the integral of the boundary part of n du dn minus u dn minus u dn du dn. And this is integration over ds. So just by replacing the different functions, so Laplacian u, so I will assume here that d equals 1. So to simplify the notations. So Laplacian n this is minus delta Dirac, so this is u of y. So Laplacian n is plus v, so this is minus 1 over v of the integral of u. So n, the Laplacian of u, this is simply equals to minus 1. So this is equal to minus. So this is minus the integral of n. So we have to integrate d volume. So plus this quantity. And this has to be equal to the boundary term, which is n du dn. So this is n du dn du dn. So we have to integrate here only over the absorbing part of the domain, which is d omega a. And this has to be, and the other term is minus, so this is equal. So the other term is simply d, and there is no other term because the rest is 0, because dn, by definition, dn is equal to 0. So we will we'll see that the integral of u over omega is simply a constant. So we call c equals 1 over omega integration of u over the domain. So this is the integral of u dv, and then this is 1 divided by the volume. So we are now going to use this identity about so we are now going to use this identity taking now y inside the absorbing window. So in that case, we will be left with the following remarks. So since the integral of the Green's function, this can be shown that this integral of dvx, this is bounded function as epsilon, or the size a goes to 0. So as a goes to 0, this quantity is bounded. So then to match the leading order term for y in the absorbing window, we are left with the following integral equation, which is integration of the Green's function n x of y. So we will call j of x dsx. So I call j of x, this is the flux, which is du dn. So this has to be equal to minus the constant. And so if we now take the leading order term of the Green's function, so we know that nx and y equals to 1 divided by 2 pi x minus y plus a regular term in x and y for y in this absorbing on the boundary. And the reason of 2 pi here, not 4 pi, is due to the image charge. So here r is a regular function. So I'm going to regular in the sense that so let me state it differently. It's not a regular function, but the asymptotics of r compared to this first term is much the singularity is much less than 1 over x minus y. And it has a singularity, as we will see, or as a singularity when x is also on this on the boundary. So we are now going to use this singularity with the fact that the flux. So what is known is that the flux j of x can be written as 1 over, so a is the size, the radius of the disk, minus r square root, and here we have a constant which we are going to call it c tilde. The reason for this, it comes from the flux through, so if you remember the electrified disk problem solved by Weber in 1870, when you put a two-dimensional disk on a plane in a 3-dimension, this is exactly the flux through this absorbing disk. And this was shown, this is derived in the book of Crank about diffusion. This is 1975. So now what we need is simply to take this quantity and replace it in this integral equation here. So for this, what is needed to be calculated is the integral of 1 over 2 pi of x minus y multiplied by this constant c tilde divided by the square root of a square minus r square. So r square and multiplied by the surface, which is simply 2 pi r dr. And this we have to integrate from 0 to a. And in here, we'll assume that the position of y is the origin of the disk. So y equals 0. So we have here the disk on the surface. And x is simply, so the module of x equals r. So with this, we need to calculate this integral. And this is direct calculation because the r, which is here, so this is simply r. So r and r goes away. And we simply have to integrate this quantity, which is the classical arc sinus. And so this has to be equal to the constant minus c. So this is equal to minus c. So now we can find the link between c and c star and c tilde. So by definition, by calculation, we'll get c tilde equals minus 2c divided by pi. So now what we need then is the calculation, the estimation of the compatibility condition, which say du dn equals minus omega. And this is by definition the integration from 0 to a, which is the radius of the flux, which is du dn, which is by definition c tilde divided by a square minus I r square multiplied by 2 pi r dr. And again, this is a direct calculation which gave us, so this is a square minus r square square root, which we have to integrate between 0 and a. If we differentiate this, we'll have, and then we have to multiply by 2 pi. With a minus sign, so which leads to c star multiplied by a multiplied by 2 pi. This has to be equal to minus omega divided, so here the diffusion coefficient is equal to 1. So finally we get c equals minus pi divided by 2 c tilde, which is equal to minus omega divided by 2 pi multiplied by minus pi divided by 2. So which is simply omega divided by 4. We have forgotten here the a. So then if we have a diffusion coefficient, we'll get c equals omega divided by 4 AD. So we can now come back to the representation of the mean first passage time as u of y equals a term of order 1 plus the integral of the flux of the Green's function multiplied by the flux, which is du dn. This we have to integrate over the absorbing part, plus the constant, which is omega, the volume, divided by 4a d. So if we take, and this is integration over ds. So if we take a point y, which is far away from the boundary layer of the absorbing patch here. So if we're outside a ball inside the domain of the absorbing part, this is also of order 1, and this is the leading order term. So this is going to be, so this, of course, when we are in the boundary layer, this term contribute, and this is of order 1 in the sense that a goes to 0 when a is small. So now we are interested, so this is the first part, and now we'll be interested in going into the second order part. So this require a different analysis. So now we are interested in the second term in the expression of the mean first passage time, that is tau is omega divided by 4dA. This we have seen. And now we need to find out the second term, which is log of 1 over a multiplied by here the mean curvature. And this is divided by, so this is divided here by 2 pi. So this is 2 pi. Okay, so for this, what we need is, and so plus O of order 1. So what we need for this is to look at the solution, the Green's function, with the term on the boundary. So this I will do. So I will stop in here for the moment and resume in the next class. I will resume the calculation here of the curvature, the mean curvature, and this the term where it comes from.